Option B for attendance, okay? So for attendance poll, choose option B, okay? And I'll leave that open for a few minutes, and then we'll okay. I've posted homework 4. Homework 4 is online now. That covers floating point numbers as well as some root finding and unidimensional, coordinate descent optimization, which we will cover in today's lecture. So you guys should be able to get through that. In Wednesday's lecture, we covered root finding methods. Root finding methods is all about finding where the function crosses 0, okay, without having to solve for it algebraically or analytically. And today we will talk about, today's topic is unidimensional optimization, okay? So unidimensional, of course, means one variable, one dimension, one variable. So we are going to do optimization of one variable. And optimization is all about finding a local, let me have your attention, please. A local minimum or maximum. So optimization is all about trying to find where there is a local minimum or maximum in a function. And we will start this off with functions of one variable. Okay? So, some applications of unidimensional optimization. Include maximum likelihood estimation, or OLS, ordinary least squares regression. Okay, and we can tell these are optimization problems because it talks about the maximum or the minimum, the least, right? And so you guys all covered MLE in what, 100B? Have you guys done that? Okay, so you find the likelihood function and you find the location of the parameter, the value of the parameter that maximizes your likelihood function, right? So MLE, just a quick MLE refresher. You guys groaned when I asked that question. The idea is you find the likelihood function of your data okay? And your likelihood function is a function of the parameter, right? So maybe it's the parameter mu that you're looking for, the parameter p or theta or whatever it is. So the likelihood function is a function of the parameter, and the goal is find the value of the parameter So for example, find the value of mu or p or theta, whatever it is, that maximizes the likelihood function. So if your data is, something like x1 through x sub n, then the likelihood function is going to be the product of each probability of x given some value theta, right? And then so we want to find argmax of theta of our likelihood function. Okay, and this is going to be your MLE estimate. I don't know. I just did this very quickly because I'm assuming you got the thorough treatment in 100B. Okay, so you create your likelihood function, okay, which says what is the probability of getting my data if my parameter is, 7, okay? And then you say, well, what's the probability of getting my data if the parameter was 8, right? And what's the probability of getting my data if the parameter had a value of 100, and things like that. And the probability or that likelihood of your data will change, and you want to find the parameter value that gives you the greatest probability, the maximum likelihood of your data, and that's going to be your maximum likelihood estimate. Does that sound familiar? Okay, that's okay with everybody? All right, so how do we do something like this, okay? So in 100B, how did you maximize your likelihood function? What did you do? Right, you took the derivative, well, you probably, because it's a product and it's hard to differentiate the product, you probably said, okay, well, let's do the log, and then it turns the product into a sum. And you say, well, that's okay because we're not actually going for the actual value. We just want to find the location of the maximum, and the value that maximizes the log likelihood is going to be the same value that maximizes the likelihood, right? So you take the log of the function, you then take the derivative of that, you set that derivative equal to 0, and then you solve for the parameter theta or whatever it is that you're looking for, and you say, well, okay, this is the value that gives me tells me where the derivative is equal to 0, so that's got to be a local min or local max, right? So let me just kind of recap of 100B. Of 100B, MLE is something like this, right? You find the likelihood function, and then what did you do is you took the log of likelihood function just to make the have a sum rather than a product. And the idea is that, all of the observations are independent, and that's why the product worked in the first place, right? Okay, so you took the log of the likelihood function, then you took the derivative of the log likelihood. You set that equal to 0. And you solved for the value of theta that made the derivative of the log likelihood equal to 0, right? And so this, the value of theta will then be a value that that corresponds to a local minimum or maximum. I'm hoping this sounds familiar. Maybe you guys just took a test on it. I don't know. Okay, so that's the analytic approach, right? Doing this derivative stuff and setting it equal to 0, all right? So in the computational numeric methods is we are going to avoid some of this analytic approach in this step, okay? So this step will be replaced with a root finding algorithm. Okay, so you solve for the value of theta that makes the derivative equal to 0. Just replace that with a root finding method, and now we have a kind of a computational approach to our maximum or minimization problem. Does that make sense? Okay, so all of those methods we learned on Wednesday about how to find where the function crosses 0 can now be used in the context of optimization or minimization. All we have to do is just find where the derivative equals 0. So, this is the computational approach to optimization. Is let's say we want to optimize a function g of x. We want to optimize a function of g of x, okay? Well, we have to do some math, okay? So we will take the derivative of g of x, okay? So we will call g prime of x equal, and we'll call this f of x, okay? So let the derivative of g of x be f of x. Then we use a root finding method on f of x, okay? And the roots of f of x will equal the critical points of g of x, okay? So these will all correspond to local minimums, local min, local max, or saddle points, right? Okay. So I'm going to just do kind of the most commonly used one is going to be the Newton-Raphson method for optimization. We just adapt Newton-Raphson for root finding, and we adapt it for optimization, okay? But technically, any of the root finding methods that we covered on Wednesday can be applied here, okay? So if you want to, if you're able to take the derivative of g of x, then you can apply any of those root finding methods, okay? So, so just to recall, so Newton-Raphson for root finding of f of x, okay? So we've got some function f of x, and we want to find the roots. We said the next iteration, the next guess, x at n plus 1, is going to be our current guess, x sub n, minus basically the run of that triangle, which is going to be x of n minus, and we said this is f of x divided by the slope of f of x, the slope at that point. Oh, sorry. All of these are x of n's. Okay. So this should be in your notes, Wednesday's notes. Okay. So that's Newton-Raphson. Oh, you know what? Let me close the poll here. Oops, I don't know what's going on. All right. Okay, and then let's do, all right, so that's Newton-Raphson for root finding. Okay, let's do Newton-Raphson for optimizing g of x, okay? All right, so we will let g prime of x equal to f of x. All right, so we're going to do basically the exact same algorithm. Basically, we want to find the roots of f of x, and these will equal the critical points of g of x. All right, so we'll say x of n plus x at time n plus 1 is going to be x at time n minus f of x at time n divided by f prime at time x at time n. Okay, and we can just kind of replace, well, if f of x is g prime of x, okay, then what would f prime of x be? F prime of x would be g double prime of x, right? Okay, so we can, if we want to write it in terms of g, we will have x of n is x of n plus 1 is going to be x of n minus g prime xn and g double prime xn. And that's it. And basically, you can take any of the other root finding methods, and if you apply it to a derivative of a function, then it's now an optimization. Okay. If you wanted to implement this into R, so what must be true about G? So G does have to be twice differentiable, right? So G does need to be twice I don't know how to spell differentiable. Something like that, okay? You need to be able to take the derivative twice. All right, and then so your function g is going to be a function of x, and inside of it, basically, you get blah 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 blah, but you're going to return a vector of 3 values, right? Return g of x, g prime, and g double prime. So you'll return a vector of three values, and then inside your algorithm, basically somewhere in there, you'll have x new is going to be what? X old minus g, it's going to be g of x old, the second value, which corresponds, so right, this is the first, this is the second, and this is the third value. So it's going to be gx old divided by gx old, the third value. Something like that. Okay, are there any questions on this? Sounds good? Makes sense? Okay, so the only drawback with this approach, this is a perfectly valid approach, right? You take the derivative of the function and then you find the roots of that derivative. Okay. The only drawback is sometimes you have a function where it's difficult to compute the derivative. Okay, difficult to get the derivative in a form where you can do f of x instead. Well, you have a few. You have a few workarounds. One is to kind of estimate the derivative by taking a small, a tiny delta. So if you think about the, all right, so what if you can't take the derivative, right? Can't take the derivative of f of x, right? Or you don't know how, okay? You can, this is like the computational approach, computational approximation. All right, and this comes from, all right, so what was the definition of the derivative? The derivative d dx of f of x, this is equal to what? The limit of f of x plus delta minus f of x divided by delta as delta approaches 0, right? Okay, and so basically all you're going to do is just going to turn this into a function, and then you'll just choose a tiny little delta, right? So the computational approximation is you'll do, we'll call this f prime is going to be a function of x and delta, and maybe the default value of delta will be 1 e to the negative 6 or something like that, okay? Oh, I'm sorry, and it's a function of f and delta. Oh, wait, no. Function of f, x, and delta. Those are, you need 3 things, right? You need the function, and you need the x, the location where you're going to find your thing, and then you need the delta size, okay? And we'll say the default to delta will be 1/1,000,000th, okay? But maybe you need something more precise. Okay, and then basically you'll just say the numerator is f of, and then x plus delta minus f of x, okay? And then the denominator will be delta, and then return the numerator divided by the denominator. Boom, okay. And now you have a way to approximate, whatever you call this thing, the derivative, okay? So now you have a way to approximate the derivative. Now, this will work for well-behaved functions, okay? Of course, to make it kind of more robust, you could have, you can say, you could have another option, okay? So like a better version is you'll have a second numerator. A numerator 2 is going to be f of x minus delta minus f of x, okay? So basically you're approaching the derivative from the left-hand side and the derivative from the right-hand side, and you want to make sure that those two things are in agreement, right? And so it gets a little bit tricky, so you're going to have to do some kind of check to make sure that numerator divided by delta and the numerator 2 divided by delta, that those things are similar in value, right? Oh, I'm sorry. And then, so if you're doing x minus delta, you have to divide by, the denominator would be negative delta, right? So you're basically approaching it from the left and you're approaching it from the right. And you want to make sure that those two values are in agreement. And if they are, then return that, and that will be your derivative approximation, okay? But if they're not in agreement, then maybe you want to return back an error and say it's not differentiable or something, right? I don't know. I'm just making this up as I go. So, but this is kind of like an approximation, right? And then there's a bunch of questions like, what is in agreement, right? And you have to say like, is, you know, one divided by the other, is that within like 1% of each other or something? I don't know. Okay, so it definitely makes it more complicated. This is like the simplest version, but you know, this is just the derivative from the kind of the right hand side. So anyway, that's what we have. Okay, so that's what we can do if we can't take the derivative of f of x directly. Another approach doesn't deal with derivatives at all, no derivative approximation, and this one is called the golden section search method. Okay, and this requires no derivatives, or approximations of derivatives. All right. Okay. Whoops. What is you guys know the golden ratio? It's like we give it phi. I don't know. Phi shows up for like a bunch of stuff, right? The golden ratio is like you have a square and a rectangle, and basically the proportions of, if this is 1, 1, and x, then the ratio between 1 plus x over 1 is equal to the ratio between x over 1. Okay? And it, did I do that wrong? It's 1 over x on this side. The long edge over the short edge is the same. Okay, and then so you get something around x is, I don't know, 0.618. Okay, and so basically 1 divided by 0.618 is approximately equal to 1.618. And the true golden ratio is, you know, whatever value this is, 1 divided by that number is equal to 1 plus that number. So, all right, so this is how the golden section search will work. It's purely numeric, no derivatives, no need for approximations of derivatives. So let's say you've got some kind of function here, and we want to find the minimum of this function. Okay. So I'm going to say here is, if there is A and B and C is somewhere between A and B, okay, and this is basically if actually let me relabel these points. Sorry. we'll call this the left, L and R, and I'm going to just say this is some point B, okay? And so B is in between L and R. And then if the function at B is less than the function of L, and the function at B is less than the function at the right, there must be a local minimum between the left and the right. Okay, so we can say that, right? So if you got, function at L, f at L, f at R, and f at B, we know that there must be a local minimum between L and R, okay? And we're going to actually pick 2 points in the middle. I don't know how to do this. Get it? So B is supposed to be at, the golden ratio, 0.618 of the way from L to R. I'm trying to eyeball this, and it's really hard. Okay, so we'll say this is B. So I'll call that B. And then if I go the other way, and if I go from R to L, and I go 0.618 of the way from R to L, this will be point A. So we're going to have 2 points in the middle, and they're each kind of the golden ratio of the way from one end to the other. So I'm going to have two points in the middle. And I'm going to evaluate the function at each of these spots, f at A and f at B. Let me go to the next slide. Okay, so we want to go, so here's L, here's R. We're going to go about 62% of the way from L to R, and go about 62% of the way from R to L, and this is going to be point A, okay? So the B is equal to L plus the golden ratio times R minus L, okay? Where phi is approximately 0.618. Okay, and A would be equal to R minus the golden ratio times R minus L. Okay. All right, and then we evaluate f at A and f at B. Okay, so in our picture, if we look at this, it appears that, f at A is lower than f at B. So f at A is less than f at B. Okay, so this establishes a new triple of points, such that we know that, so this gives us a new, quote, triple of points. Okay, this will be L, A, and B, where L is between, A is between L and B, and f of A is less than f of L, and f of A is less than f of B. Okay, which means there must be a local min between L and B. Does that make sense? So we've already evaluated f of L, and we've evaluated f of A and f of B. And if f of A is smaller than f of B, then we know that there must be some point between L and B where there's going to be a local minimum, because A is less than f at A is less than f at L, and f at A is less than f of B. Okay, so there must be a local minimum. If we had the opposite, then A, B, and R would form a new triple of points. Okay, so if we had the opposite situation where it went like this, and you had A and B and R here, okay, then A, B, and R would form a new triple. Okay, where f of B is less than f of A. Okay, and so what this means is we will change our boundaries. So basically we're going to just revise our search and eliminate this section. This part we throw away, and so now we have L becomes L, but then B becomes R. Okay, B becomes the new right boundary. And here's the genius of the golden ratio, is that A will become the new B, because if we go from, if A is, the golden ratio from R to L, so it was like 0.618, it's technically what, if this is at 0 and this is at 1, then B is at 0.618, and this is at 0.382. Is that right? Okay. 0.382 is the golden ratio squared. Okay. And so now I would just need to find a new location here. So the left boundary remains the left boundary. The B becomes the new right boundary, and this point A becomes the new kind of midpoint for B. And so let me just kind of cut and paste this. So here we've got this. Okay, so now we're dealing with this smaller area. So this we rename to be R. This will become B. And then now I need to figure out a new A, okay? And so A will be, I don't know, this is going to be 0.618 minus 0.382. I don't know what that is. Something around 0.236, okay? And so what this allows us to do is that with the golden section search, we do not need to recalculate B and f of B. Okay, we just use the values for A, values of A and f of A from the last iteration. Okay, so we don't need to recalculate this value, this location B, and this value of f of B. Okay, so we just use the values from the last iteration. Okay, we do need to find the new A. The new A and the f of A, of the new A. Okay. But, you know, if your function is quite complicated, and maybe it's computationally expensive to calculate the function at a certain location, then you want to minimize how many times you have to calculate new points, right? So we're not just arbitrarily picking 2 points in the middle. We're purposely using the golden ratio to take advantage of the fact that at the next iteration, we can reuse this point. Okay, and so that's beneficial, right? Because this is a computationally heavy method in that we didn't calculate the derivative, and so it's probably a function that is a little bit difficult to deal with. Otherwise, we would have just taken the derivative and used one of the other methods. But if we got a function that's kind of hard, we want to avoid making repeated calls to calculate the function, because maybe the function takes a while to compute. Okay, so to kind of summarize how this goes about, okay, so basically, kind of the golden section search. Okay, so you'll need a function f, a left, and a right. Okay, and so we'll let a equal L minus the golden ratio times R minus L, and let B be A is R minus this, and B is L plus this, R minus L, okay? And then evaluate f of A and f of B, okay? If f of A is less than f of B, basically the new triple is L, A, and B. So L becomes L, B becomes R, and A becomes B. And then the new A will become, basically, now that you've recomputed L and R, this is going to be R minus phi times R minus L, okay? Use new values of L and R, okay? And then if it's the other way, f of B is less than f of A, the new triple is A, B, and R, okay? So R becomes R remains R, A becomes L, and B becomes A, and then the new B will be L plus phi times R minus L, okay? And then repeat. So you just keep iterating through this whole process until the difference between your left point and your right point, the difference between L and R, goes below some tolerance threshold. Okay, maybe they get within 1/1,000,000th of each other, and then you say, okay, I'm satisfied. This has got to be where my minimum is. Sounds good? Okay, so this is covered in your homework, and in the homework, there's something called coordinate descent, and I guess I'll talk about that briefly on Monday, and then we'll cover more stuff. Okay, we'll introduce simulation and topics like that. Okay, all right. Have a great weekend, you guys. We'll see you guys in a few days.